Welcome back. Today we will still talking about the functions, and today we will have two main definitions. One of them is surjective functions and the other one is bijective functions. So in the last video, if you haven't watched the last video, please go back and watch the last video which we talked about the injective functions, and in this part we will talk about the surjective function. So what's a surjective function? So we will start with a function from A to B is said to be surjective, and sometimes it's called onto. So either surjective or onto if this has happened. Put it in a box. If for every y in B, you will find an x in A such that f of x is equal to y. This means anything in the codomain, anything in y, anything in B will have to get an x goes to this y. So that means we will hit everything in y. Everything in y is an output. So if we do it here in the arrow diagram, this means if this is A, this is B, it means nothing left behind. Nothing is not mapped into. Which means if this is A, B, C, each one of these must have an arrow comes to it. It must be. Maybe 2 arrows, that's fine. Maybe 3 arrows, that's fine. But at least there is an arrow goes to everyone in the output. This is the meaning of the surjective. Which in another word, if we go back to the introduction topic, this means the codomain, which is equal to B, is the same as the range. You remember the range is the actual output. This means the actual output is everything in B. Everything in B will be in the range. So this is the definition for the surjective. I would like you to pause this video, think about it, memorize it, make sure you understand it, because it's a very important topic and we will use it many times. It says that if you have any y in the output, any y in the codomain, there must be an x in the input in the domain that mapped to this y. And as we did in the injectivity, we have the question is how we will show that a function is surjective, or how do we show a function is not surjective. So in order to show a function is surjective, the good news is we have 3 easy steps. The first step is we will take any y in B, arbitrary y. If B is the integers, we will take any integer, we call it y. And then we will write y equal f of x, and hopefully we will try to isolate, we will try to solve for x. We want x to be in one side alone and the y's on the other side. The final step, we need to check that my x is actually in A. Sometimes you will get an x because you will write x equal y over 5, but then x is not in your input. Something maybe else you get. So you have to check that your x is in A. So if you do those steps, you will get exactly that the function is surjective. So take any y and try to find what is x there, and we will do it through reverse engineering. We will assume y equal f of x, and then we will try to find my x. So it's kind of, we use what we know or what we want to get. Of course, if we want to show the function is not surjective, We will try to do those 3 steps and see if something goes wrong. What could be wrong is that we cannot get an x. We try to find x. Maybe we find x, but x is not in number 3, and maybe we cannot even can isolate x. So something will go wrong, and we will know the function is not surjective. So I think now we are ready, if we use those 3 steps, to do the first example, which is example number 5 up here. So we want to show this function that take an integer x and give me the output is x plus 1 is surjective. So if we follow the steps that we just talked about, the first step we said that we need to take any y in B. So I will take y to be in Z, and this is arbitrary y. No condition, no information. Step number 2, we need to write y equal f of x. So y equal x plus 1. And now what we need to do is we need to isolate x. We need x to be in one side. So if we want x to be on one side, we take the 1 to the other side, we get x equal y minus 1. So far, so good. Third statement, let me check. X is in Z, which is A, the input. Y, X, and Z, let me just analyze it here. X equal y minus 1. This one here is integer. Of course, the 1 is integer. Integer minus integer as a whole will be integer. So indeed, x is in Z. This is just a quick proof, because integer minus integer is integer, so we are assuming everything is fine, and that will give me the proof for the surjectivity. Hence, the function is surjective. So please pause the video and take a look at the steps from the top to the bottom. If I go through them very quickly, if I want to show a function is surjective, the first step, I will take any y in the output, and then I will write y equal f of x. But I know what is f of x. It's already given to me here. It is x plus 1. Next step, you need to isolate x. So x will be y minus 1. This will take care of step 1 and step 2. Step number 3, now you get x. Check that x lives in the output, which is integer. How do we check x is in the output? We analyze what is x. X is y minus 1. Y is integer, 1 is integer, and if you take a minus between two integers, you get an integer. So x indeed an integer, and this will show me that the function is surjective. The next example, we want to show that the function is not surjective. So as I said before, showing a function is not surjective, we need to see what will go wrong if I try to prove that my function is surjective. So just let me do, I don't know, maybe I'll just divide this into two sides here. And let's see if we do the 3 steps, what will go wrong. So let y in Z, arbitrary, any y, I don't know which y, write y equal f of x, so y equal to x. Next, isolate x. So x equal y over 2. Number 3, if we continue the same way as before, this is just analysis. Sometimes it gives me a help. If we go as before, we need to check x is an integer. Well, we have to write what is x. X equal y over 2. Let me zoom in. Now, this is integer, and you divide it by 2. Do you always get an integer? Well, this is something maybe correct sometimes, maybe not. For example, if y equal to 6, the answer will be 3, so it is integer, no problems. How about if y equal to 5? This will give me 2.5, not integer, so I have a problem. Even if y equal to 1, I have another problem. Even if y equal to 3. So there are some problems can happen. I don't need to write all the problems. I just need to find one problem. So what's the best option? I will say let y equal to 5. Then no x integer such that y equal f of x, because 5 equal to x has no solution in the integer. So all what you need is to find one bad example. That's all to show that the function is not surjective. We'll go to the last example now for the surjectivity before we move on to the bijective function. The last example, as I said, we want to practice slowly but study the idea of a function from power set to power set. So here I will take a power set of A to the power set of A. I will take any subset as input, and the output will be the complement of X. Now, is there anything gonna change? The answer is not. Why? Because the first step, I will take y in the output, which means arbitrary subset of A. Step number 2, we need to write f of x equal to y. What is f of x? Is x complement equal to y. Now, how can I get rid of this complement? Of course, the idea is easy. Take the complement for both sides. And we know that subset, the complement of the complement is the set itself. And here we get y complement. Step number 3, check x is in the input. Now, what is x? X is y complement, which is, of course, a subset of A. Why? Because y is subset of A. So remember, the complement is those elements which are not in A itself. And that would show that this function is surjective. Hence, the function is surjective. Okay. Next, please take a rest and watch the next part, which will be about the injectivity. So bijective. What is bijective? We know what is injective. And we know what is surjective. Now, what is bijective? So we say a function f from a to b is said to be bijective. And sometimes we call it one-to-one corresponding. F is injective and surjective. Simple as that. So everything we did before, we just need to put it together. That's all. So it is injective and surjective. And we will call it bijective. So it should be straightforward and direct. So bijective is containing the injective, which is what we did in the previous video. Please, if you didn't watch it, go and watch it. And surjective, if you are not sure, you can just replay this video from the beginning and you will see the definition of surjective. If we combine both of them, we get what we call it bijective or one-to-one. Clear why it's one-to-one? Because it's injective. And corresponding, because it's surjective. Corresponding means everything is correspond to something. Now, in terms of an arrow diagram, things are very beautifully going. Each one has one arrow and only one arrow, and we don't leave anything behind. So one from here and one from here, they all correspond to each other. So one input, one output, one output, one input. Nothing left behind, nothing without an arrow, everything goes only one and only one arrow from each of the sides. Before I come back and write the notation, I would like to do one quick example to show that a function is surjective. So we will need to show that this function, which take input anything except number 1 and give me an output which will be anything except number 2, is bijective. So remember, to show a function is bijective, this is a task to do two things. We need to show the function is injective, and we need to show that the function is surjective. So each part will do its own thing. So we need to show that the function is injective. So we, as usual, we will assume f of x1 equal f of x2. Hopefully we'll do many steps and we will reach that x1 equal to x2. Now what is f of x1? F of x1 is 2 plus x1 minus 1 equal 2 plus x2 minus 1. Of course, the first thing I noticed is x2 with 2 get cancelled. So you will get x1 minus 1 equal x2 minus 1. Now if we do just quick algebraic manipulation, this means x2 minus 1 can go there, x1 minus 1. Just this one. Now I think I can cancel the 1. And finally, I would reach where I want to reach, which is x1 equal to x2. Hence, f is injective. We finished from the first part, which is the part that we need to show that the function is injective. Let me do the second part. And for the second part, let me do it with a different color. Maybe that would be easier for you to distinguish. surjectivity if we want to say it is. How to show the function is surjective? First of all, take any y in the codomain, so everything except 2. So y is any real number except 2. Keep this in mind, we will need it. Second, we said we have to write y equal f of x, which means y equal 2 plus x minus 1, 1. And the next step, we need to isolate x. Let's see what we get. This is easy. The first step, I take the y to the other side. I get x minus 1. Now, if we flip the right-hand side, you get x minus 1. If you flip this around. Also, you have to flip this one. This is over 1. So it will be 1 over y minus 2. And I think finally, x will be equal to 1 plus y minus 2. Now, third question is check x is a real number except 1. So I don't need to use 1. First of all, we notice something. Is x a real number, or do we have a problem because of we have a denominator? Of course, remember y is not equal to 2, so we have no problem of the denominator. Let me write this down. Y is not equal to 2, hence no denominator problem. So x is a real number. We don't have a problems. It will be a real number. Now, the only thing I need to check, make sure x is not 1. Check x is not 1. Now, how do we check x is not 1? Well, the idea is, let's see. Suppose x equal to 1. Let's see, can x equal to 1? Well, if x is equal to 1, then it will be 1 equal 1 plus y minus 2, which means 0 equal 1 over y minus 2, which is false. I can't have 0 on the left side equal 1 over something on the right side. So this is always false. So x is not equal to 1, hence the function is surjective. Hence f is surjective, and so bijective. And that's how we prove that a function is injective as well as surjective. So it has to go through the steps. We need to go through them as they are, but this is the general idea. One thing before I conclude this video is some notation. The first one, and the most famous one, is sometimes we write A kind of equal, but it's kind of equivalent to B if there exists a bijective function. So we write something like this if there is a bijective function. Thank you very much for watching. By this, we conclude the section about injective, surjective, and bijective. The next video will be about composition of